Okay, so in single variable calculus, you're probably familiar with the chain rule, right? So in single variable calculus, what the chain rule basically tells you is that if you have a function y, which is an f of x, and if in turn x is a function, x is some function of t, then dy over dt is related to dy over dx by so dy over dt equals dy over dx times dx over dt. Now, this is in single variable calculus. Now, it is almost as if you can treat the derivatives like fractions. You can think of the dx and the dx cancelling out and giving you dy over dt. They're not fractions, but it is almost as if you can treat them as fractions. Now what we'll do is we will look at the chain rule in multivariable calculus. Chain rule in multivariable calculus. So let's look at a statement of the chain rule. What does this chain rule look like in multivariable calculus? So let's say you have a function. This is z is a function of x and y. Z is a function of both x and y, and this is differentiable, right? And remember, we looked at the definition of differentiability in the previous lecture. Now, if z is a differentiable function of x and y, then you have and if you have x equals gt and y equals some function of t, meaning z is a function of x and y, and x is a function of t, and y is a function of t, then z is essentially a function of t only, right? Then z is essentially a function of t only. Remember, so this is differentiable. Right? And of course these are also differentiable. These guys are also differentiable. Okay, so if that is the case, then if you want dz over dt, this equals dz partial z over partial x times dx over dt plus partial z over partial y dy over dt. Now, why is this a total derivative? Why is this a total derivative? And why is this a total derivative? Because these are total derivatives because x and y are functions of t only, right? So x and y are functions of t only. All right. So let's do a diagram to tell you how things work. Let's draw a flowchart. So z is a function of not exactly a flowchart, but what's its branch diagram, I guess. Z is a function of both x and y, and again x and y are both functions of t. So this gives us, so you move along this branch, you get these partial z over partial x times dx over dt. You move along this branch, you get partial z over partial y times dy over dt. And then you add both branches to get dz over dt equals partial z over partial x dx over dt plus partial z over partial y dy over dt. Okay? So now how do we know that this is true? Meaning, how do we prove this chain rule? So if you remember the definition of a differentiability, the definition of differentiability from the last chapter, you have if let delta z be a small change in z. Let delta z, this is a small change in z, and delta x is a small change in x, delta y is a small change in y. Then delta z can be written as actually it doesn't have to be small, right? It doesn't have to be small. Let's just call it, let it just be a change in z. So then delta z can be written as partial f partial x delta x plus partial f partial y delta y plus epsilon 1 delta x plus epsilon 2 delta y. Of course, delta x and delta y are changes in x and y. And you have delta x comma delta y. These guys go to 0 as epsilon 1 epsilon 2 as these guys go to 0. Right, now if that is the case, then delta z over delta t equals partial f over partial x, sorry, this should be dx over dt plus df over dy delta y over delta t. And of course, okay, and then you have the terms with the epsilon 1 delta x over delta t, and then the next epsilon 2 delta y over delta t. Now let's take the limit as delta t goes to 0, meaning what happens when this is very small? Well, let's take the limit on both sides. There's limit delta t goes to 0 df over dx delta x. Okay, in fact, we can write the limits on the right hand side as df over dx times limit delta x over delta t as delta t goes to 0, and then you have plus df over dy limit delta t goes to 0 delta y over delta t plus epsilon 1 delta x this epsilon 1 okay, so these two limits, in fact, since epsilon 1 and epsilon 2 are functions of x and y, we can write these as products of limits, right? So, limit delta t goes to 0 epsilon 1 times the limit delta t goes to 0 of delta x over delta t. Remember, this is from the product rule for limits, right? Product rule for limits. So this can, and of course the last term is limit as delta t goes to 0 epsilon 2 times the limit as delta t goes to 0 of delta y delta t. Again, this is due to the product rule for limits. Okay, so remember what happens to this. So this is by definition, the left hand side is by definition dz over dt, and this is by definition limit df over dx times, this is by definition dx over dt, total derivative of x with respect to t, and the second term is of course a definition dy over dt. Now remember, this goes to 0, this goes to 0, and this goes to 0 as epsilon goes to 0. So this goes to 0, tends to 0, and this also tends to 0. So we are left with the first two terms only, and this is the chain rule, right? So we've proved the chain rule for the scenario where x is a function of x, and for scenario in which both x and y are functions of t. So let's look at an example. The first example we're going to look at is we have z equals x square y plus 3 x y to the 4, where x equals sine twice t, right, and y equals cosine t. We want to find we want to calculate dz over dt. What is dz over dt? Now there are two ways of going about this. We could just plug in the value of x. You could plug in the value of y, and you would get dz over dt. But instead of that, but that would be pretty lengthy, right? So instead of that, what we do is we use the chain rule. Okay, so let's draw a diagram, right, to see how they're related. So z is some function of x and y, right? So z is some function of x and some function of y, right? And x and y, from x you get a sine twice t, and from y you get cosine t. Sine twice t, and from y you get cosine t. So what is dz over dx? Well, this is equal to dz over dx is twice xy plus 3y to the 4, twice xy plus 3y to the 4, and dz over dy is z over dy is equal to x squared plus 12xy cubed. X squared plus 12xy cubed. 12xy cubed. And dx over dt is then to cosine twice t, and dy over dt is then negative sine t. And so in that case, you have dz over dt equals 2xy plus, remember, dz over dt, we have our formula, which is dz over dx times dx over dt, right? Plus dz over dy times dy over dt. And you just plug this in, plug all of this in. Dz over dx is twice xy plus 3y to the 4. Dx over dt is 2 cosine twice t, and of course this you could write as x squared plus 12xy cubed, and this you can write as negative sine t. And you get dz over dt. You can always write it in terms of t if you wish, which is entirely up to you. Okay, now the second case of the chain rule, of course we're looking at a different scenario here. The chain rule, case 2, right? So case 2, which is the in case 2, your x and y are functions of z and t. So in the chain rule case 2, chain rule case 2, in this case what happens is that z equals fxy is a differentiable function of x and y, but then h is a x is a differentiable function of s and t. X is a differentiable function s and t. Y is a differentiable function of s and t. So you said x equals say x equals g of st, and you said y equals h of st, right? So let's try applying the theorem. Let's try applying the chain rule case 1 here, right? So so in this case, since h is a function of both s and, since g and h are functions of s and t, we will get partial z over partial s, right? Now remember, this is not in this. Now we calculate partial z over partial s. Why do we calculate partial z over partial s? It's because, remember, z is now indirectly a function of s and t. In the previous scenario, in case 1, z was a function of t indirectly only, right? Now z is a function of both s and t. So this is equal to partial z over partial x times partial x over partial s plus partial z over partial y times partial y over partial s. Now this is the same, and of course with t you get partial z over partial t equals partial z over partial x times partial x over partial t plus partial z over partial y times partial y over partial t, right? It's very easy to show this on a diagram. Z is of course a function of x and y. Z is a function of x and a function of y. X and y are both functions of s and t. St. Right, so you so this derivative is partial z over partial x. I mean, you go along this line, you take the derivative of z with respect to x. You go along this line, take the derivative of x with respect to s. Go along this line, you get dx over dt. Go along this line, get dy over ds. Go along this, dy over dt. Of course, dz over dy. So you end up with so let's say you want to calculate dz over ds. So you go along this branch, right? Plus go along this branch, and you get and you get the first expression, right? I want to calculate dz over dt. You go along this branch, plus you go along this branch via y. First you go via x, then you go via y, and you get dz over dt. Right? So it's easier when you do it using a diagram. So for example, we want to calculate dz over dt, where z equals e to the x sine y. And this example is again from the book. So if z is given by, z is given by z is given by e to the x times sine y, and x equals st square and y equals s squared t. How do we find dz over ds and dz over dt? Remember again the chain rule. Dz over ds equals dz over dx, dx over ds plus dz over dy, dy over ds. Remember, this is partial derivative, partial derivative, partial derivative, partial derivatives, not total. This is important, right? And you just plug them in, and you get a partial derivatives, right? And of course, you can always substitute z as a function of t, and you can always substitute x and y as functions of t to get your derivatives as functions of t, right? So functions of s and t. Sorry, x and y are functions of s and t, so you can just substitute them to get your derivatives as functions of s and t. So so you can work this out yourself. So your independent variables are of course s and t, right? So at the bottom of this chain, you get your independent variables. These are your independent variables, and these are your x and y, just x and y. These guys over here, these are your intermediate variables. Variables, right? And of course z is your dependent variable. And the tree diagram will always help you remember the chain rule. Just keep that in mind. The tree diagram is going to help you remember the chain rule. So let's okay, so how do we do the chain rule? How do you apply the chain rule here? You draw branches from x to s and t and y to s and t. If you want So for each branch we have the corresponding partial derivative. So to find dz over ds, we add the products when you go along the x branch and the y branch. When you go to s, z to s along the x branch, z to s along the y branch. To find dz over dt, you go from z to t along the x branch and z to t along the y branch, and you add the corresponding products of partial derivatives. And of course, if you want the general version of the chain rule, right? Let's do the general version of the chain rule. So let's say you have a scenario in which z is a function of n variables. Z is a function of n variables. Okay, let's close this. General chain rule. Right, and we have m independent variables, right? So from z you get n intermediate variables, right? And each of these guys, so x1, x2 and xn are all differentiable xn, right? Functions of t1 tm. Now, if that is the case, there are n intermediate variables and m independent variables, right? Now, so z is then so you have z. Let's draw a diagram for this. You have z, and from there you have x1, x2, and then dot, right? So you have x1, have x2, x n intermediate variables, and from here you have and for example for x1 so each of x1, x2, x3, x4 all the way to xn, right? So each of these depend on t1, t2, t3 all the way to tm. This depends on t1, right? tm, t1, tm, right? So let's say you want to find dz over dti. What is the value of dz over dti? Well, how many ways are there for you to go from z to ti? So dx1, so dz over dx1, dz over dx2, dz over dx. And so how many ways can you go from z to ti? Well, you can go through x1, dz over dx1, dx1 over dti plus dz over dx2 times dx2 over dti dz over dxn over dti. So this is a general version of the chain rule, and using this we can formulate the chain rule in any for any number of intermediate variables and any number of independent variables. So for example, if you have a situation in which W equals f of x, y, z, t, W equals f of x, y, z, t, and x equals x uv, y equals y uv, function of uv, and z equals z uv, and t equals some t uv. So let's and we want to find, let's say, partial w over partial u and partial w over partial v. How do we find this? Well, first thing we do is we draw a diagram with branches, right? So w equals f of x, y, z, and t. Well, you start with w on top. W is the dependent variable, and this leads to x, y, z, and t. X, y, z, and t, each of which depends on u and v. So x depends on u and v, y depends on u and v, z depends on u and v, and t depends on u and v. uv, 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 uv. If you differentiate along this branch, you get dw over dx. Differentiate along this branch, you get dx over du, and so on and so forth. So this is dw over dy, this is dy over dv, and this is dy over du. There's not enough room, so I won't write all the derivatives. So this is dx over dv, and so on and so forth. What is dw over du equal to? dw over du. So how many ways can you go from w to u? Well, we could do dw over dx times dx over du. You could do dw over dy times dy over du, and you could do dw over dz times dz over du. And of course, then don't forget dw over dt times dt over du. There are 4 possible routes to u. You could go through x, you could go through y, you could go through w, you could go through t. And similarly, dw over dv equals dw over dx, dx over dv, plus dw over dy, dy over dv, plus dw over dz times dz over dv, plus dw over dt times dt over dv. Again, 4 possible ways you could go from w to v. Now, of course, this can be generalized to functions of with any number of intermediate variables and any number of independent variables. Please have a look at examples 5. Okay, this is examples 5, 6, 5 and 6 on page 988 and 989 of Stewart's Calculus. Okay, so now we're going to look at something that you've already seen before, implicit differentiation. Right? So implicit differentiation is when a function is implicitly defined, right? So for example, you have something along the lines of x squared plus y cubed sine y equals y cubed sine y equals 0. Well, from here it's impossible to write y as a some function of x, right? Some function of x. So in single variable calculus, what we are used to doing is that we are used to differentiating both sides with respect to x. So you would have differentiating this guy would give me twice x. Differentiating this would give me y cubed cosine y dy over dx plus 3y square dy by dx sine y equals 0, and you would make dy over dx the subject of the formula. So there's another way to look at this in terms of partial derivatives, right? So so let capital F be a function of x and y. Let capital F be a function of x and y, and we have something along these lines: f of xy equals 0, and we have y is some function of x, right? So if we were to draw a diagram for this, you would have something along these lines. You'd start with f, and then f would be a function of x and y, and then y would be a function of x again. Now, in this scenario, x plays the role of both an explicit variable, of both an intermediate variable and an independent variable. Okay, so x is the independent variable, y is an intermediate variable. So how would you find? So let's say I wanted to find dy over dx, right? Dy over dx, and in order to, so x is of course just a function of x. Now, what is this equal to? df over dx. Actually, not this. I want to find this df over dx. Well, this is actually equal to 0 because the right hand side is 0. Now I can find I can use this to find a total derivative, because remember, f is ultimately a function of x. So I can write the total derivative of f with respect to x. So then this would be equal to partial f over partial x times, so this is times dx over dx. So you'll have dx over dx here, plus partial f over partial y times dy over dx, and of course this is equal to 0. Right? So dx over dx is of course 1. This is partial f over partial y, dy over dx. So then dy over dx equals negative partial f over partial y divided by partial f over partial x, where partial f over partial x is not equal to 0. Remember, partial f over partial x is not equal to 0. So this is another way of looking at implicit differentiation, right? This is another way of finding dy over dx. So, I mean, total derivative of y with respect to x. So, for example, if you have x cubed plus y cubed equals twice xy equals 6xy, right? So x cubed plus y cubed equals 6xy. Then of course we have x cubed plus y cubed minus 6xy equals 0. So capital Fxy in this case is given by x cubed plus y cubed minus 6xy. And then, now since it's impossible, it's very hard to make y the subject of the formula here, what I would do is I would find dy over dx equal to negative, which is equal to f of y, f sub y divided by capital F sub x, and of course f sub y is equal to 3y squared minus 6x. Of course, don't forget the minus sign, and f sub x is equal to 3x squared minus 6y. Right? So that will be my dy over dx. Okay, now if z is a function, so let's say x and y are independent. So let's say we have a function now, g, which is a function of x, y, and z, but z is actually a function of x and y, right? So x and y are the independent variables here. In that case, using the chain rule, dg over dx, right? Total. Okay, so let's draw a diagram first before we find the before we find the partial derivatives, right? So you have g. Now g is a function of x, y, and z is of course a function of x and y. Or x and y are independent of each other, right? In this case, so you have x, y, z. X and y are independent of each other. We're not going to relate them. So x is a function of x only, y is a function of y only, and z is a function of x and y. So this tells me that dg over dx, for example, okay, so we can't write total derivative x over total derivative g over total derivative x, because remember g is now a function of both x and y. So what we have to do is we have to write partial g over partial x. This is of course equal to partial g over partial x times dx over dx when you go along this branch. G over partial x dx over dx. Then you have partial g over partial y, dy over dy, partial g over partial z, partial z over partial x, right? So plus. Okay, so along this branch you can't go along. You can't get to x along this branch, but you can get to x along this branch. Get g over partial z divided times partial z over partial x, which of course, now if g x y z equals 0, then you have if this is equal to 0, then you have then what's going to happen is that you are going to have this equaling 0, meaning when you take the partial derivative of both sides, you get 0, and since this is equal to 1, actually this should not be written as partial derivative. This is this. Okay, let's put it this way. So if this is 0, because otherwise this is going to. If this is 0, then this is going to be 0, right? So this is not exactly partial derivative. So what we're doing is essentially we're taking the derivative of both sides with respect to x, right? Both sides with respect to x, right? So you have g x y z on one side, you have 0 on the other, and this is what you end up with. So so in that case, actually, what is partial z over partial x equal to? Z over partial x is equal to negative gx over gz, right? And similarly, you can show that partial z over partial y equals negative gy over gz. Now, if you differentiate both sides with respect to x or y, one side is going to give you 0 and the other side is going to give you this. That's how you get negative gx over gz or negative gy over gz. This is okay, so one example of this is, of course, example 9 on page 991, where you have x cubed plus y cubed plus z cubed, right? X cubed plus y cubed plus z cubed plus 6xy z equals plus 4 equals 0. I want to find partial z over partial x and partial z over partial y. I could take this to be my gxyz, gxyz, and what they've also told us, I mean, of course, okay, so in this case, z is implicitly a function of x and y. Remember that z is some function of x and y. Right, so dz over dz, dz over dx, remember, is negative gx times gy. Sorry, over g sub z. Sorry, g sub z. So on the left hand side you have your g. So gx is of course going to give me thrice x squared plus 6yz, and gy is of course going to give me 3y squared plus 6xz. Oh, no, so sorry, this is gz, not gy. Gz. I'm going to find gz. So gz is going to give me 3z squared plus 6xy. Right. So this is how you would do implicit differentiation. And similarly, you can also find partial z over partial y, which is equal to partial z over partial y equals negative gy over gz, since z is of course an implicit function of x and y. Okay, so we are done with the chain rule now. So we move on to section 14.6, which is the directional derivative, right? So when we found, for example, when we were working on derivatives with partial derivatives with respect to x and with respect to y, right? We were we were thinking about derivatives that have derivatives that are in the x direction or in the y direction, right? Meaning where only x or y changes, right? So now we look at direction. So we want to look at how a function changes in any direction, right? So for example, the example that's given in the textbook, let's say you have a temperature function, right? It's a function, temperature is a function of position. So you have a temperature in an area, temperature is a function of position, Let's say you want to go, let's say you want to see how, temperature changes when, instead of going along the x or y directions, let's say you want to see how temperature changes when you go along an arbitrary direction, right? So for example, you're in a, just a moment. so you're here, right? And this is your room. This is the y direction. This is the x direction, right? Now if you wanted to find how temperature changed when you went and let's say T is a function of x and y. Your temperature is a function of x and y. So if you wanted to find the rate of change of temperature when you were going right, you would find let's say you were going along this direction, rate of, so let's say this is direction 1, let's say this is direction 2, and let's say this is direction 3. So when you're going along direction 1, right, direction 1 is parallel to the x direction. When you go along direction 1, right, rate of change of temperature with respect to direction, sorry, with respect to position, not direction, with respect to position, is partial derivative t with respect to x, right? When you go along direction 2, you would have partial t over partial y. I mean, this same quantity would be partial t over partial y. But what for direction 3, which is not in the direction of x or in the direction of y? How would you find the rate of change of temperature along that direction? For that, what you would do is you would use something known as a directional derivative, right? Directional derivative. So let's say you want to find the okay, so let's say you start with okay, so let's recall the definition of partial derivatives, right? So f sub x at x naught y naught, f sub x at x naught y naught, this is equal to the limit as h goes to 0 of f x naught plus h y naught minus f at x naught y naught divided by h, and similarly f sub y at x naught y naught is defined. Now how would you find the directional derivative in the direction of u? So let u be a unit vector, right? So let u be unit vector. Let this guy be a unit vector. Right? Now the directional derivative of f in the direction of u, let's define this, right? The directional derivative of f, this is a definition. The directional derivative of f in the direction of u is given by This is given by d sub u of f x naught y naught equals the limit as h goes to 0, right, of f of x0 plus ha. Actually, let's write this down now on a new page. So the notation is this: d sub u of f at x0 y0 equals the limit as h goes to 0 of f of x0 plus ha comma y0 plus hv. Remember, a and v are the components of the unit vector u, minus f of x0 comma y0 divided by h. So if f is a function of two variables, we can look at the geometric meaning of this of the directional derivative, right? So let's say you're on the surface, right? So this surface is z equals fxy, right? This is surface x. This is given. Sorry. This surface is given by z equals fxy, and we want to move in the direction of u, right? And if this is the direction u, then we're moving along this. Then we take the plane that contains u. Remember when we found f sub x and f sub y, we took a plane that was parallel to the x or the y-axis. Now we take a plane that is parallel to u, and we look at the intersection of that plane. I mean, of course, the plane is parallel to u, and it passes to the point where we are taking the derivative, which is x naught, y naught, z naught. We look at the intersection of the plane with the surface, and that gives us a curve C. And the tangent to that curve, the gradient of the tangent to the curve, is our directional derivative, because it tells us how the curve changes when we're moving in that direction, right? So the gradient of this tangent, gradient of this tangent is the directional derivative. Okay, so let's look at a few examples of directional derivative. And so this is the definition. And of course, in the directional derivative, if you set a equals 1 and v is equal to 0, you get partial f over partial x. If you set v is equal to 1 and a is equal to 0, you get partial f over partial y. So the directional the partial derivatives with respect to x and y are of course examples of the directional derivative. Okay, so let's find out a way to get the let's look at a theorem, right, that will help us calculate this directional derivative. So we have a definition, but the definition isn't very useful, right? But let's try a theorem, right? Let's look at a theorem that will help us calculate the directional derivative. Okay, so and this theorem will motivate us to introduce the gradient vector. So if f is a differentiable function, remember it's always differentiable. Differentiable function of x and y, right? So f is a differentiable function of x and y. Then the directional derivative, let's call it the dd, of f in the direction of the unit vector u is given by du d sub u fxy d sub u equals fx xy a plus fy xy b. So this is a theorem. This is a theorem. And of course, a theorem is something we need to prove. Okay, so let us say that g of, let us define a function. So we start the proof. This proof is actually given in Stewart's calculus. So let's define a function g of h, right, as f of x naught plus ha and y naught plus hb. Then g prime of h, sorry, g of 0 equals f of x naught y naught and g prime of 0 is the limit as h goes to 0 gh, of course this is 0 plus h, minus g of 0 divided by h, by definition, right? Because h, remember, is g is a single variable function. It only depends on h. So this is equal to limit as h goes to 0 f of x naught plus ha comma y naught plus hb minus f of x naught y naught divided by h. But this is by definition. By definition, this is equal to du of f at x naught y naught. Alright, by definition. On the other hand, if you recall, gh, okay, now we can also write gh as f of xy, where x equals x naught, x is defined to be x naught plus ha, and y is defined to be y naught plus hb. So we may write g prime h. So let's look at another way of writing g prime h. This can be written as, of course this is defined to be dg over dh when you already see. So prime, the expression function prime is only, the notation is only valid when we are dealing with functions of a single variable. So g is essentially a function of a single variable. So with the chain rule, this is actually equal to partial g over partial x times partial x over partial h plus partial g over partial y over partial h. So remember, you have g, you have x, y, and both are functions of h. Right? So as a matter of fact, instead of partial x over partial h, you can write dg over dh, and here you can write dy over, sorry, dx over dh, and here you can write dy over dh. So this becomes partial g partial. Now what is partial g over partial x? Partial g partial x is the same as fx at xy. Why is that? I'm sorry. Partial g partial x times dx over dh. It's partial. So this guy over here, so this should, g prime h. This is actually the same as partial f partial x times dx over dh, because remember gh is this, right? Plus partial f partial y dy over dh. Of course, then this is equal to now what is dx over dh? Dx over dh is a, and dy over dh is b. Right, so you have df over dx a plus df over dy times b. Right, and you set and this is at where is this at? This is at general xy, right? Xy, general xy. But now when you set h equals 0, then x equals x naught and y equals y naught. So g prime of 0 equals partial f over partial x at x naught y naught times a plus partial f over partial y at x naught y naught times b. And remember, we have another expression for g of g prime 0, which is du f of x naught y naught. So in that case, so du of f at x naught y naught equals partial f over partial x at x naught y naught times a plus partial f over partial y x naught y naught times b. So this is exactly what we've been trying to prove. And of course here u equals av is a unit vector. U is a unit vector. So in particular, sometimes in general, if you use a unit vector, then you could write a equals cosine theta, v is equal to sine theta, and you would get u to be a unit vector, right? So then this would be df over dx at x naught y naught times cosine theta plus df over dy x naught y naught sine theta. So you'd have your fx x naught y naught cosine theta plus f sub y at x naught y naught sine theta. Right, cool. So so example 2 on page 997 tells us to calculate the directional derivative with respect to in a particular direction of a certain function. So let's have a look. Example 2. Okay, so you have fx equals x cubed minus 3xy plus 4y squared. So we want to calculate the directional derivative in the angle given by the angle theta equals pi by 6 measured from the positive x-axis, right? So the vector that we're talking, the unit vector we're talking about, of course, has components cosine pi by 6, cosine pi by 6, and sine pi by 6. And then du fxy is this times cosine pi by 6 plus this times sine pi by 6. Now fx is given by this is of course thrice x squared minus thrice y, and this is negative 3x plus 8y. That's exactly what we've plugged in here. And you of course, and you plug in the values of cosine pi by 6, which is square root of 3 by 2, and sine pi by 6, which is half. and you get this answer. And now if you want to calculate it at the point 1 2, well, you just plug in 1 2 and you calculate it at the point 1 2. And since we're on the surface, and fx, if you were on a surface, then you plug 1 2 into this, and you get 1 minus 6 plus 4, right? 1 minus 6, sorry, plus 16, I'm sorry. And then of course you get your z value, right? Okay, so and so at 1 2, the value is 13 minus 3 root 3 by 2. Okay, so now we're going to introduce something called the gradient vector. Okay, the gradient vector, denoted by grad f, gradient vector. Well, we call it grad f, or this upside down triangle is known as a nabla. We call this del f, right? Del f, right? So del f, if f is a function of x and y, is defined by partial f partial x I plus partial f or partial y j. This is del f, right, of x y. Now our this is a vector. This gives me a vector quantity. The motivation for introducing this notation is that the directional derivative along the directional derivative along u was defined as, so this is at xy, fx xy times a plus fy x y times b. This is kind of defined as del f. So this can be written as partial f over partial x I plus partial f over partial y j dot ai plus b j hat. Alright, and this can, of course, this vector is del f, and this vector is u. Right, so this can be written as del f dot u. Now, grad f times grad f dot u. Okay, cool. So now, if we, for example, if you want the directional derivative of a function, let's look at example 4. You have a function x squared y cubed minus 4y, and we want to find the directional derivative in this direction, 0.2 minus 1. So what you need to do is, of course, you need to find the unit vector first. Find the unit vector along this direction first. Right, and that is given by u v over the size of v. Right, the size of v is of course equal to square root of 29. You divide by the square root of 29, you get the unit vector, which is my u, and you do, so du f at a certain point, 2, negative 1, is del f dot u. So del f at, what is del f at 2 minus 1. Del f is equal to so df over dxi plus df over dyj, which is equal to this, as you can calculate, and when you plug in 2 minus 1, you get negative 4i plus 8j. So you find the dot product, and this along that direction. This is the partial. This is the directional derivative. And similarly, you can define directional derivatives for functions of 3 or more variables. So du of f of x, y, z is given by f of x naught plus ha, comma y naught plus hv, comma z naught plus hc, minus f of x naught, y naught, z naught, divided by h, and then you take the limit as h goes to 0, if the limit exists. And remember, this has to be equal to 1. A squared plus b squared plus c squared equals 1. This is the unit vector. And of course, in general, we may write du f of x0, right? So x0 is this has many components. This is a vector. So x0 can be x naught, x1 naught, x2 naught, all the way to xn naught, right? This is a vector function. These are not powers, by the way, not powers. These are labels. So this is equal to f of x naught plus hu minus f of x naught, right? So these are functions that take in vectors as arguments. And similarly, the directional derivative is fx xyz times a plus fy xyz times b plus fz xyz times c, and the gradient vector is defined as f sub x xyz, comma f sub y xyz, comma f sub z xyz, and we can find the direction derivative by dotting the gradient vector with the directional vector, right? So this vector gives you the direction, and this vector is the gradient, grad f, right? Example 5, again, f of x, y, z equals x sine y, z. So del f is this, and u, of course, is v over the modulus of v, which is I plus 2j minus k, divided by 1 plus 4 is 5, with the square root of 6. And of course, you would find the dot product of del with the of del f with u, and that will give you the value of the directional derivative. Alright, so now we look at a theorem. Right? The theorem tells us that, let's say we have a function of 2 or 3 variables, right? And we want to find a direction in which the directional derivative is maximum. In what direction is the directional derivative maximum? In what direction directional derivative maximum, right? So if you're in 2 or 3 dimensions, then actually, let's say you have a unit vector u, right? And we want to find du d sub u of f at x0, y0, z0, right? And where is this how do we maximize this? We maximize this. Well, then du of f of x0, y0, z0 is a dot product fx times a plus, so this is actually equal to fx I hat plus fy j hat plus fz k hat, and all the derivatives are evaluated at x naught, y naught, z naught, comma. Okay, let's call it u for unit. Let's not include the hat. Comma u. But then this is equal to del f, right, times u modulus of u cosine theta. But since this is 1, since this is a unit vector, so this gives me modulus of del f cosine theta. This is the length of del f, of course, at x naught, y naught, z naught times cosine theta. Now when is this maximum? This is maximum when cosine theta equals 1, max 1, which means theta equals 0, which tells me that u and del f are in the same direction. Okay, so the theorem. So what we know now is that if u and del f are in the same direction, then the directional derivative is maximum, which means that the directional derivative in the direction of the gradient, the directional derivative is maximum when we are moving in the direction of the gradient. In other words, u is parallel to del f x naught, y naught, z naught. Right, that's when the directional derivative is at its maximum. Let's look at example 6. So you're given fxy equals xe to the y. We want to find the maximum rate of change at of f at the point half comma 2, at the point as f of the maximum rate of change, right? So in the direction of the greatest vector, so sorry, not at half comma 2, I think it's at 2 0, sorry, at the point 2 0, at the point 2 0, right? So delta f at 2 0 is equal to sorry, not delta f, del f at 2 0 is equal to so partial f partial x is e to the y, so e to the y comma x e to the y at 2 0. This is equal to e to the 0, which is 1, and x e to the 0, which is 2. And the unit vector in this direction is of course given by square I plus 2j over the square root of 5, right? So it's going to increase. So the maximum increase is I plus 2j over the square root of 5, and the maximum rate of increase is the modulus of del f. Remember, if cosine theta is 1, right, so the rate of change is the modulus of del f. So that's the maximum rate of increase. And you could carry out a similar calculation in 3 dimensions. Okay, so at this point, let's look at a new way to calculate the tangent plane. So recall that we calculated the tangent plane by finding the perpendicular to a surface. I'm sorry, the perpendicular. So we found 2 tangent vectors, right? Fx and Fy, and we found 2 tangent vectors using the partial derivatives, Fx and Fy, and we found the cross product to give us the tangent plane. Okay, so let's say we have a surface S given with so let's find another way. So let's say we have a surface S given by f of x, y, z equals k. This is big F, and this is where. So this is what is known as a level surface, right? This is a level surface of a function of 3 variables, meaning with this this function is at a is equal to some constant, right? So let's see. So we have S. So this is the surface S that is given by f of x, y, z equals k, meaning it's implicitly defined. And let C be any curve that lies on the surface S and passes through the point P. Remember, we spoke of curves that pass through our point, but back then we were only speaking of curves that move in the x direction and the y direction. Now we're going to deal with curves that move off in any random direction, right? So RT that, remember, any curve can be parameterized by one variable, t, right? So now let RT naught equals x naught, y naught, z naught, meaning t naught is the point at which r is equal to at t is equal to t naught at the point P. Okay, and C is a curve that lies on S, of course. The entirety of C is on S, right? Notice that this curve is on S. So for C, this has to be true. F of x naught, f of xt, yt, zt equals k. Now you can use the chain rule. Let's use the chain rule, right? And when we use the chain rule, we have partial f. Actually, let's say we want to differentiate both sides with respect to t. So df x y t z over dt equals dk over dt. This is 0 since this is a constant. F going from x, y, z. All of these are functions of t, and then this then becomes partial f over partial x, dx over dt, plus partial f over partial y, dy over dt, plus partial f over partial z, dz over dt. This is equal to 0. Now notice something here. Partial f over partial x, partial f over partial y, partial f over partial z. These are the components of del f. And these guys, they're basically the vector x prime t, y prime t, z prime t. And the dot product of these guys is 0. Dot product of these 3 guys is 0. And of course, f of x naught, this can be written as this vector, right, x prime t, y prime t, z prime t, may be written as x prime t. If you recall, this can be written as t, a sum r prime t. Remember, this is a vector in the direction of the tangent. I mean, this is not the tangent vector. The tangent vector is, of course, this vector divided by its magnitude, but this is a vector in the direction of the tangent, in the same direction as the tangent. And since we're dealing with dealing with a particular point, we're dealing with a point that is we're dealing with a point x naught, y naught, z naught. So we may write this as delta f x naught, y naught, z naught dot r prime t equals 0. Remember, this is a vector and this is a vector. And the dot product is equal to 0. And of course, this equation is tells me that the gradient vector is perpendicular to the tangent vector to any curve C that passes through P. Right. So the gradient vector, which is del f, right, is perpendicular to any tangent vector. The gradient vector is perpendicular to any tangent vector. So this is a tangent vector, this is a gradient vector. But the gradient vector is always on the same. The gradient vector at a particular point is constant, right? Well, delta f at x naught, y naught, z naught is always in the same direction. So the gradient vector is actually perpendicular to the tangent vector to any curve that passes through P. So if you had another curve, right? Let's call it C1 that went in this direction. So let's say you'd call it, the tangent vector would be R1 prime at T naught, right? Or you have another curve, right, C2, and you had R2 prime at T naught. So the gradient vector will be tangent to all of these tangents. So the gradient vector will be perpendicular to all of these tangents. So what does that tell me? That tells me that the gradient vector is perpendicular to all the tangent vectors, and hence the tangent vectors, they form a single plane. Right? The tangent vectors to all the curves passing through a point, they form a plane, a tangent plane. Right? So and using of course we found an equation 1257. We wrote the gradient of the tangent vector as, so we wrote the equation of the tangent plane as, remember, fx x naught, y naught, z naught times x minus x naught. So here we're dealing with capital F, fy x naught, y naught, z naught, y minus y naught, right, plus fz x naught, y naught, z naught times z minus z naught equals 0. So this is a dot product. So, and of course the normal line passing through P and perpendicular tangent. Okay, so normal line to S at P is the line passing through P and perpendicular to the tangent plane. Of course, the direction of the normal line is given by the gradient vector. So remember, any line in 3 dimensions, right, in the direction, let's say u equals avc, right, can we give and passing through x naught, y naught, z naught can be given as x minus x naught by a equals y minus y naught by b equals z minus z naught by c. So the line parallel to the tangent to the gradient is given by x minus x naught by fx, y minus y naught by fy. This is your a, this is your b, and this is your c, because these are the components of the gradient vector. So for example, we have so you want the equations of the tangent plane and the normal line to the surface given by x squared by 4 plus y squared plus z squared by 9 equals 3 at the point -2, 1, -3. So this is my capital F, X, Y, Z, and I can so Fx, I have Fy, and I have Fz, and using these three I can find the equation of the tangent plane. And once I found the equation of the tangent plane, and of course, and I mean this is basically delta f dot r prime t is equal to 0, t naught, sorry. And we can find the equation of the normal line at t naught, at this point. So this is x plus 2 divided by fx, y minus 1 divided by fy, z plus 3 divided by fz. Now we have the normal line. Okay, so let's have another example which is telling you the same thing. Okay, so what does the gradient vector give you? The gradient vector, since we haven't looked at contour plots, we're not going to go over this much, but the gradient vector, what it tells you basically is that it gives you the directional it gives you the fastest direction rate of change, right? The modulus of the gradient vector gives you the fastest rate of increase of f. The dot product with u, of course, gives you the rate of change in the direction of u, and del f, remember, del f is perpendicular. So if you have a surface given by f of x y z equals some constant, then del f is normal to the surface. Right, so these are three very salient points. These are it just gives you the significance of the gradient vector. You can also show that if you have a curve given by f of x y is equal to constant in 2 dimensions, then del f is normal to f always. Okay, so that's that for this lecture on sections 14.5 and 14.6. We have covered the chain rule, and we have looked at the directional derivative and the gradient, and we have what we've done is we've tried to look at the usefulness of the gradient. So this is something we're discussing further in this course. So the gradient, the symbol nabla, is something we need for we will keep on coming back to again and again and again in this course, right? So thank you very much. That's the end of this lecture.